The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, molecules have three kinds of structures: electronic, vibrational, and rotational. And my goal is to give you a sense of how do we predict each kind of structure. Not how do we calculate it, but how do you have it in your head so that you know what are the expected patterns and how do you use one pattern to help you with a decision about what another pattern means. So electronic structure is a combination of big stuff and small stuff. The big stuff is basically the spectrum of hydrogen or the spectrum of H2 plus molecular ion. That these are patterns, one kind of pattern that is possible to remember, but the more electrons we have, the more complicated that will be. But it's useful to have a simple picture of what it ought to be and how it gets disguised. But there are little things, too, that also provide crucial clues what the electronic structure is, like fine structure, right? Hyperfine structure, spin orbit, spin rotation, things where the spectrum gets a little complicated, but it's really small splittings. And often they tell you a lot more about the nature of the state you're looking at than the big stuff. And so you want to be able to deal with both. And so I'm going to present my unique view of atomic spectra with the view of making it useful to you for understanding what you're going to encounter in molecular spectra. So,
Bob, can I ask one quick question now?
Yeah.
So we talk about electronic, vibrational, and rotational structure.
Yes.
And typically only these three. And by electronic structure, we really mean like valence electronic structure. So it basically, right?
Yeah.
So it is the reason we don't talk about spectra of core electrons because it's experimentally hard to make X-rays, or is it because it's really not as interesting? And similarly, do we not talk about like the nuclear magnetic resonance type spectra because it doesn't really affect these other motions, or because you need a big magnet?
The simple answer, we don't talk about them because I don't know them, like as well as I know these other things. The core structure, when we excite to very highly excited electronic states by opening up the core, the molecule is never stable. And so you end up having continua. But in some ways, the core structure is simpler. Because the cores are really, they don't know they're in a molecule, or they only know they're in a particular molecule through fine structures. And so they are wonderful probes of the chemical nature of a particular, the chemical environment of a particular atom. And that is useful, but it's not complicated in the sense that assigning a spectrum is complicated. Basically, you know where each shell has its spectra, and each atom has its different end shells at different energies, and so it's not, you don't need me to help you to assign such spectra. Those are very easy. It's the kind of spectra that most people who are not physical chemists think all spectra would be. Things that are very, very low resolution, very simple to interpret, and have direct chemical significance. NMR is of great importance, usually for larger molecules where you want to know what's connected to what. The kind of thing that I'm talking to you about is you know pretty much what the bonded network is, and you have some ideas about what the structure of the molecule would be. there may be times when you have spectra of different molecules, and you'd like to sort them out according to which is which. And in that sense, NMR might be of use, but usually nobody does NMR in the gas phase because it's a magnetic dipole Lau transition. It's weak, and you need a lot of molecules in order to get an NMR spectrum. So I think the communities who use core structure and NMR are different from the physical chemists, mostly, that are going to be concerned with the spectra of small-ish molecules in the gas phase. But that was a really good question. Okay, so we want to ask two questions when we approach a spectrum. What do we expect, and when should we be surprised? Because if the spectrum is entirely what we expect, well, then there isn't really any challenge, and there isn't anything new. But if we're surprised, you need to know you should be surprised, and that the molecule is telling you something that it's worth figuring out, because it's violating some rule, or it's doing something really neat. And so being surprised is good. And so I'm going to begin talking about patterns of levels, transitions, and we're going to talk about good quantum numbers and things like that. Okay, but the way we're going to start, we're going to talk about one-electron atoms. In other words, hydrogen atom, helium plus ion, lithium 2 plus ion. And these are all really simple things, but they illustrate that electronic structure doesn't have to be a telephone directory. It can be just a bunch of related things, and if you know one, you know the others. And then life gets more complicated when we go beyond one-electron atoms. So we're going to talk about one-electron atoms, the terms in the Hamiltonian, the basis functions we use to express the Hamiltonian, various kinds of scaling rules that tell you how properties depend on quantum numbers, some notation, and transition propensity rules. For example, we have the atomic angular momentum J, and for a transition, and the atomic orbital angular momentum L, the propensity rule says that delta J ought to be equal to delta L. J changes by +1, L changes by +1. You can have things violating propensity rules, but the stronger transitions are this, and you get that from a vector model. And I'll introduce you to a vector model, which is the beginning of using these precessing vectors, or things that usually, when you start to see them, you say, I want out of this room, because I don't really know what these vectors are and why I'm forced to memorize these things. Okay, so after we do one electron atom, we'll do alkali atoms. And those are atoms with one electron outside of a closed shell. And they differ from the one electron atoms in an important way, a simple way, and that's the first step into complexity. And we'll eventually get to many electron atoms, and then we have to do more work to relate what you see in the spectrum to the things you'd like to understand. And once we get to alkali-like atoms, there's going to be a little bit of quantum defect theory. It's a topic I'm going to come back to repeatedly in increasing sophistication. Basically, as chemists, we know about quantum mechanics a little bit. We know about Hamiltonians. And most of my approach to the problem is in terms of effective Hamiltonians, which are just a toy version of the real thing. There is another approach which is more of a physicist approach, which is scattering. And there is a way of using scattering to learn about the structure of things, and that's where quantum defect theory comes in. And it's more powerful for certain classes of problems, and we'll see that. Okay, so bottom of page 1. The one-electron atoms are called hydrogenic, so the Hamiltonian is a function of spherical polar coordinates and spin coordinates, which are just something that we don't really know what they are. But so it's a central force problem, and central force problems are all related. And the Hamiltonian is expressed in this way. We have c squared over r cubed to u squared c squared. So this is the kinetic energy, this is the potential energy, and this is my very good friend spin orbit. It's an example of small stuff that helps you a lot in understanding what's going on. So it's perhaps an extra level of complexity, but it's something that we care about. Now, one of the neat things you notice right away is this is 1 over r cubed. And so that actually turns out to be a very important simplification, because it says spin orbit, whatever that is, happens near the nucleus. And we don't care that much about what's going on outside. So it is, if it's happening near the nucleus, it's where things are pretty simple. And so this is why it's such a valuable probe. Okay. Kinetic energy. Well, there are some things, a lot of things in the kinetic energy, and one of them is angular momentum. So we have orbital angular momentum that's included in here. And when we write a basis set, which includes L as one of the quantum numbers, that part of the angular momentum has this form. We still have r squared as a variable, but this is now a quantum number, and this has taken the L, taken the angular part of the problem out, and we have now something that, although it comes from the kinetic energy, we stick it into this, the potential energy, and we say we have an effective potential, which is a function of r alone. And so it's a central force problem which has been dressed up with something that has some angular momentum. And so we say this generates a centrifugal barrier. Why is it a barrier? Because it's positive, and as r gets small, this gets big. And so it's a barrier that keeps the electron from getting in close to the nucleus. And you would, yes. Okay. So we have a central force problem, and the wave function can be written as a product of two factors. An angular factor and a radial factor. Now, for all central problems, you get the same angular factor. And so this is universal. And this radial factor is unique to the particular atom, but not when you have one electron atoms. It's basically the same thing. It's only scaled by the charge on the atom. So this, for one electron atoms, this is universal, but generally the wave function is divided into a universal angular momentum factor and a system-specific radial factor, which is where all the interesting stuff is, but a lot of the manipulations get done here. Okay. So, C is charge on the nucleus. Yes?
Could you just remind me how we actually include like that spin orbit term into the Hamiltonian? Because I guess like I'm still thinking like potential energy and kinetic energy. Just
Well,
how we
okay, the Hamiltonian is the energy. And so anything that contributes to the energy of a state gets put into the Hamiltonian. So you're right to say, I know where this comes from. This has to do, it's actually a relativistic effect. But the convenient thing is that it behaves as L dot S, the orbital angular momentum dotted with the spin. And it's the angular momentum and the spin of the same electron. And so I'm not going to derive these things. I'm going to tell you, because, you know, many courses you see the lengthy derivations and you don't see what they're for. So this is just a contribution to the energy that happens for atoms and molecules. There are other smaller contributions like hyperfine, where you have the electron with its orbital and spin angular momentum and interacts with the angular momentum of the nucleus. And that's NMR. Well, that's not. That's
well,
ESR.
can we think about this as a like potential energy of the spin being in the magnetic field created by its own rotation? So on this.
You can do that, but it's a little bit dangerous because, you know, we associate a magnetic dipole with the orbital angular momentum and with the spin. And so this looks like a dipole-dipole interaction. But it isn't quite, because when it's a relativistic effect, it has to do with the electron moving very fast near the nucleus. And I can't really explain it any better than that. And it scales with the nuclear charge, and a simple dipole-dipole interaction wouldn't do that. So, but if you think of it as two magnetic dipoles interacting, you get the operator form, but not the magnitude. And that's okay. So, there, you know, we're always sticking terms into the Hamiltonian because we need them, or we're taking them out because we'd just assume they weren't there. But this is a really good question. Okay, so now, I have to define some things. This is the charge on the nucleus, and so for hydrogen it's 1, and for helium plus it's 2, and I want to make a distinction. You might have a particle, well, for one electron systems, it is the charge on the nucleus, but for many electron alkali-like systems, it is not necessarily either an integer or the charge on either the ion core or the nucleus itself. And so this turns into a fudge factor in a few minutes. But for one electron systems, it's not a fudge factor. This is the reduced mass, and the reduced mass is the mass of the nucleus times the mass of the electron over the mass of the electron plus the mass of the nucleus. Now this is always really small compared to this. And so if you throw that away, this becomes just the mass of the electrons. Okay, so this reduced mass factor is almost exactly the mass of the electron. But it isn't exactly, because this is not 0. And so if you change the nuclear mass from 1 to 200, or to 100 to 200, you can do that, there will be a very, very small effect on this reduced mass. And one of the neat things is, okay, that's going to change the energy levels by an amount that's proportional to how much the reduced mass has changed. And so it changes maybe by a part in 1,000. Well, that's pretty small. But in electronic spectroscopy, we measure things typically to a part in 1,000,000. So it starts to make a significant difference, one atom versus another. So it's not just the mass of the electron. but it's so there's a little bit of stuff there. Okay, now we have two choices of basis sets, and in which we can look at this problem. And this thing here is the reason why we talk about basis sets and a choice of basis sets, and that there's one good choice and one not such a good choice. And so the uncoupled basis set is written as LML SMS, and the coupled one is written as LSJ MJ. So what is this? These are shorthand for eigenvalues of operators that commute with the exact, well, commute with each other, and they commute with the zero-order Hamiltonian if they're going to be basis functions. So the angular momentum, total angular momentum, orbital angular momentum, L squared gives you L, LZ gives you ML, etc. And J is the vector sum of L and S. So we have these angular momentum things. These are this is an eigenfunction of L squared, where the value of the eigenvalue of L squared is LL plus 1. So we don't write LL plus 1 in here. We write L because it takes less space and it's unambiguous. And the eigenvalue for L sub z is M sub L. LZ operating on this gives the function back times M sub L. So we have these building blocks, and with them, whenever we see any angular momentum in this problem, we can work out what the contribution of that is to the energy level formula. So L plus. So we can write the components of L as LZ plus LX plus LY, but we like to write things as in terms of these raising and lowering operators because they're neat, because they're analogous to the creation and annihilation operators we have with harmonic oscillators. And so L plus is LX plus LY, ILY, and L minus is LX minus ILY, and L dot S is LZ SZ plus 1/2 L plus S minus plus L minus S plus. Now, with quantum mechanical operators, you do have to worry about commutation. But I just got through saying that these come from mutually commuting operators. And, okay, well, L plus is not one of them, but L and S do commute, and the components of L and S do commute because they operate on different particles. So we don't have to worry about the order. We don't have to symmetrize. And L plus, operating on LML, it only operates on the LML part, not the SMS part, gives back LL plus 1 minus, now it's just like harmonic oscillators in a second. The non-zero matrix elements of L plus always are between one value of M sub L and over here one higher. And so what goes in here is the product of the two values of M sub L that occur in a non-zero matrix element. So you don't have to remember anything. If you know how to write, L plus increases M sub L by 1. And so you have ML over here and ML plus 1 over here if it were a matrix element. And so you have ML plus 1 minus the root times so this is a little bit more complicated than A dagger and A, but the important thing is the thing you don't know automatically is which two values of M sub L you put in here. And now you do know that. And now if we write this, we know immediately that it's going to be plus or minus 1. Okay, so the important thing is if you're going to have insights in this stuff, you don't want to be constantly looking it up in a book. You want it to be hard, you know, the stuff you need to be hardwired. So what has to be hardwired? Selection rules. L plus raises M sub L. S plus raises M sub S. They change the value by 1. L plus and S plus, LZ, SZ, none of them change the value of L. And the matrix element, or the thing you get, is the product of the initial and final quantum numbers. Nothing to remember beyond that. I mean, that's pretty simple. Okay, so we have these two basis sets, and the only angular momentum in this problem, well, there actually is 2 bits of angular momentum. I said we get this. Well, that came from L squared. Well, L squared operating on L, ML is L squared, L plus 1. Okay, so I did that without even breathing. But so there was some angular momentum that came from the kinetic energy term. But the important angular momentum is over here, and so I've written L dot S in this form, which is the way we normally do it, even though everybody knows the dot product of 2 vectors is the Z, Z, X, X, Y, Y term. But if you write it in this way, you get the plus minus, the minus plus, and the Z, Z term. Okay, and so we can, we have L dot S, and so we can write L dot S 2 different ways. We can write L dot S this way, and we can also do a trick. And the trick, J is equal to L plus S. This is vectors. Now, J squared is equal to L plus S1 squared. And so that's equal to L squared plus 2L dot S plus S squared. And so rearranging, we have J squared minus L squared minus S squared times a half is equal to L dot S. So if we're operating in the L, S, J, MJ basis set, this thing operating on that, I'll give you half J squared minus L squared minus S squared. That gives, well, these are the operators for which we have quantum numbers here. So that means no work. And we have 1/2. I'm suppressing the h bar squareds. You know, angular momentum operators always give you an h bar for every power of the operator. And why keep them? You just absorb them in constants. Okay, and so we get J plus 1 minus L plus 1 minus S plus 1 times L, S, J, M, J. So the spin orbit operator, the angular momentum part of the spin orbit operator, gives this nice compact thing, and it's exclusively diagonal. Whereas this guy, this other form, well, this is diagonal in the M sub L's and M sub S, but this is not. So if you would like to write down an operator and convert the Hamiltonian to a formula, you'd like to have the form of the operator be such that we just get a formula. No off-diagonal matrix elements, no work. And so when you have spin orbit, it's usually preferable to use this coupled LSJ-MJ basis rather than the uncoupled one. But there are many advantages for using the uncoupled basis, and it's, you know, it all comes out in the wash. You do transformations between basis sets. I'm going to teach you about that too. But right now, you know, the example is there are two choices of basis sets. One, for one, the Hamiltonian is completely diagonal. For the other, the spin orbit is off diagonal in an innocuous way, but it still leads to work you have to do. Okay, please ask me questions about this as it's going by.
Can I ask you about the H bars again?
Yes.
So, with each H bar has units.
H bar has units, right?
So, every time you apply those operators, you not only get some quantity of angular momentum, but you get...
But remember, last time I talked about, we had some matrix element expressed in terms of quantum numbers and trash.
And you can...
Now we care about the value of the trash.
Right.
But that's a separate bookkeeping matter, and that this is too. Remember, the Hamiltonian generally has energy units, but if you're a spectroscopist, it has reciprocal centimeter units. So you got a factor of HC also. So why not just stick all the stuff that you don't care about into the constant, the spin orbit constant, or whatever it is that you're going to be manipulating?
Okay, so if you apply the operators, though, different numbers of times, you end up with different units.
Well, not really, because...
Okay, so that's what I'm asking. How do you get around...
All of these terms have dimension of energy. And so, you notice that I had an L squared. Because that came from the centrifugal barrier. That has dimensions of energy when you divide it by 2 mu r squared.
Okay.
And spin orbit, L dot S, multiplied by the tensor, that has units of energy. We always have products of 2 angular momenta. And the only time you have 1 angular momentum by itself is for this, say, the Zeeman interaction. But then you have a vector, the field, dotted into the angular momentum, and so it all works out. And so, you know, people like to use atomic units where h bar is 1, and then you have to just take it on faith that people haven't given you a bum formula which doesn't have the right stuff in it, because you can't check anymore. But angular momenta always give you a factor of h bar for every time you, so this gives you 1 h bar, and this gives you h bar squared, and you can always reconstruct things, but I just don't like to write h bar a lot of times. Okay, so another way of saying some of the stuff that I said before, we have this operator L dot S, which we need for the spin orbit. And we can write a commutation rule. And we know that L dot S commutes with L squared, S squared, and J squared. And it commutes with JZ. So you can have this. This is going to be diagonal in a representation where you have L squared, S squared, J squared, and JZ. But L dot S commuting with LZ is not 0. Because you're going to get an L plus and an LZ, and the commutation rules for angular momentum says, well, that's too damn bad. You know, they don't commute, and the S doesn't help you. So if you're going to get diagonal matrix elements in some basis set, It's because the operator commutes with all of the quantum numbers, or all of the operators that correspond to the quantum numbers in that basis set. Are we all okay? All right, next is a handy-dandy formula for all the energy levels of one electron atoms. And the reason I give this formula is not because you don't know it or couldn't figure it out, but because it gives you an idea of how things are built. And as soon as we go from one electron system to more than one electron system, we're going to have to make each of these terms a little more complicated. But the insight comes in seeing how you get back to this one electron picture. Okay, so we have energy levels or matrix elements of the Hamiltonian. So we have quantum numbers, the principal quantum number, orbital angular momentum quantum number, the spin J, mj. We decided that was a better basis set than the uncoupled basis. I actually like the uncoupled basis because for doing simple algebra using ladder operators, it's always more convenient to have an operator, a magnitude and a projection for each operator, L and LZ, S and SC, but you can do much more. As soon as you give that up, as soon as you have 3 magnitudes in one projection, you have to do angular momentum transformations, 3J coefficients, which we'll get to sometime. So, but I like to always use tools that I can do in my head rather than having to look at a book. And sometimes I waste a lot of time doing that, but usually it's a good idea. So, H over trend HC and N, L, S, M. Okay, so these are the matrix elements that we're going to care about, the energy. And so the first thing that we know is that the Hamiltonian for a spherical object is spherical. It's totally symmetric. That means it cannot change any angular momentum. Therefore, we immediately write down L prime L, S prime S, J prime J, and it's a scalar. It can't even change the projection quantum numbers. So, and we're going to set the zero energy at the dissociation energy. So we're going to have a minus sign here because everything is lower than that. And now this all multiplies a factor. We have mu over me. The reduced mass over the mass. Now remember, this is almost equal to me. So this is almost 1. But it isn't quite 1. And then that multiplies 109,737. There's some more digits, but I remember 109,737. I know that, and the telephone number of the house I lived in when I was 5. But this one, I think I know, I'll never forget. So this is the Rydberg constant, and this is the big stuff in the electronic structure of atoms. So this is about 1. This is 100,000 wave numbers. And this is the charge over the principal quantum number. And it's LE dot AL, principal. It's like nuclear. If you get it wrong, you're an idiot. And the next term is the spin orbital. And that has a scale factor. And it goes to the charge to the 4th power, and the principal quantum number to the 4th power. And with n over j plus a half. Now, since I don't normally work in this way, I have to look that up. But notice we have an n here and an n to the 4th here. And so this is overall n 1 over n cubed. And almost everything in Rydberg land, which is really hydrogen atom, goes as 1 over n cubed, or 1 over n to the 3/2, depending on whether you're talking about an amplitude or a thing, an energy or an expectation value. So we have that, and then we have, that's it. So this is E, N, L, J, and I guess we lost something off the edge of the page, Z, mu. So this is the universal formula for the energy levels of a one-electron atom. Big deal. It's, you know, the energies are determined by N, L, and J, except that L is gone for one-electron atoms because of a surprising symmetry. You would have expected it not to be gone, but there's a cancellation, and so then there's a weak dependence on the charge on the nucleus. Well, not a weak dependence, a charge on the nucleus and a dependence on the reduced mass. Okay, so these are the energy levels for a one-electron atom. We have the big thing, and we have the small thing, and we have a weaker scaling with the principal quantum number and a stronger scaling with the principal quantum number. Okay. So we have the energy levels, and each of the energy levels is a state. So and the states have names, and so we label the states of a one electron atom like this. So this is the multiplicity, 2s plus 1. This is the principal quantum number. This is J. And this is an interesting mnemonic for L. The values of L can be 0, 1, 2, 3, 4, 5, 6, S, P, E, F, G, H, I, K. Why don't we put J there? Because we use J for something else. So, but everything in spectroscopy uses the alphabet, except occasionally you have to make a glitch. Okay, so
if you're at L equals 8, would that also skip out on N?
No, for some reason J is excluded, but you have L states. I don't know why. So we generally use lowercase letters for one electron, and uppercase letters when there's more than one electron. And so this is enough to completely specify a state. And okay. So we could have a spin orbit splitting, which would be 2 delta P 3/2 minus the energy of 2 delta P 1/2. And those scale according to the z to the 4th. And so the value of that splitting for hydrogen, here's some more notation. So this is called the first spectrum of hydrogen, and that's the neutral. This is called the third spectrum of lithium. The first spectrum of lithium would be lithium neutral. Second would be lithium +1. And the third would be lithium +2. And this, unfortunately, disagrees with the way chemists label things. So you just have to be careful to find out whether the atomic spectra labeling scheme is used or the chemist's scheme. Okay, now this spin orbit splitting for the 2 double P state in hydrogen is 0.37 wave numbers. For lithium, it's 30 wave numbers, and for sodium, it's 5400. And it's just reflecting the z to the 4th scale. And since it's determined near the nucleus, it's a kind of universal measure of what is this orbital that is open shell that's giving us this thing. And so it turns out to be a very, very useful signpost for what state is this? What are the orbitals that are involved in generating this state? And so, okay. So, if we have one electron wave functions, practically anything we care about can be written as some function of the quantum numbers. So if we have an off-diagonal matrix element, one can write, remember, spin can only have a value of a half, so it's silly to write it as prime. But so anyway, you could write any quantity as an explicit function of the quantum numbers, especially n. And so now what I'm going to talk about is some of these formulas for how things behave. And one of the things you care most about is the coordinate of the electron relative to the nucleus. Okay, this is the coordinate of the electron. It operates on spatial coordinates. It doesn't operate on spin. So immediately, if I write down an operator that is some function of r, it's not going to do anything to the spin part. The spin is acting like a scalar relative to this. It's just a constant. It doesn't see it. So r only operates on spatial, not spin coordinates. Now, you know about scalars and vectors and tensors. If you don't know, let me just tell you, a scalar is like a constant. It doesn't have any angular dependence, it's a number. And if you have some angular momentum representation, one of the things about it is that it doesn't care which projection quantum number you've got. When you calculate its expectation value, it's going to have the same expectation value independent of projection quantum number. A vector is, it has 3 components, and we can understand vectors. You can imagine going to something which we call a second-rank tensor, and that's sort of like a d orbital. We can classify all operators according to their tensorial rank, and that's called spherical tensor algebra. And this is useful because the tensorial rank is just like an angular momentum. And so if you're coupling an angular momentum of 1 to an angular momentum of 2, there are certain formulas for how to do that. And so it's very useful to look at an operator and say, oh, I know its tensorial rank, well, this is 1. It's like an angular momentum of 1. It couples to other angular momenta, and in a sense that it can change the total angular momentum by plus or minus 1 or 0. Because you can tell that this is like a vector, and we know vectors are rank 1. Okay, and you'll see eventually things with higher tensorial rank. Okay, another thing about this is if we ask, well, what happens to r, this vector, if we invert through the origin? It changes sign. That means it has odd parity. Parity is an important quantum number 2, and so by writing this down, you know it doesn't operate on spin, it has odd parity, and it looks like an angular momentum of 1. And so that tells you a lot about its non-zero matrix elements. So the matrix elements of this have selection rules. And the reason it can't change L by 1 is because it has odd parity. The reason it can't change L by 0 is that it has odd parity. If you take the same L twice, that's got even parity, and so the integral is going to be 0. So R by alone will change L by 1. It can't change S. Surprisingly, it can change J by 0 or plus or minus 1, and that comes from vector addition between these things, and I'll explain that. It can't change M sub S, and it can change M sub J by plus or minus 1 or 0. And N is not an angular momentum, and so you can have any change in N for this kind of an operator. Okay, so now, for hydrogenic functions, there are two kinds of matrix elements of R that we care about. One would be the operator that enables you to have a absorption of a photon, the electric dipole operator. So, in Continent Shortly, which is a wonderful book, just because it's filled with formulas, which for many, many cases, and it's also filled with obscure derivations which you mostly don't want to look at. So you just look at the formulas, and it's organized in a very transparent way. So one of the formulas is the thing that tells you about the transition from the ground state of any hydrogenic system to any possible excited state. Since we're starting in S and L can only change by 1, it's NP. So this is the transition moment squared. This is what determines the intensity of transitions, and only transitions from S to P are allowed. And this has the magnitude n to the 7th, n minus 1 to the 2n minus 5 power. You can derive these things, but you got to be nuts to do it because they've already been done. N plus 1 to the 2n to the minus 2n minus 5. And so when you look at this and you say, well, these are both just about n, and so we get n to the minus 10, n to the 7th, we get n to the minus 3, which is what you sort of expect for transitions among one electron from n equals 1 to n. And I'll soon explain this n to the minus 3 is the source of the n to the minus 3/2 scaling factor in Rydberg-Klein. I won't do that today. So then there's another table, and that's expectation values of the scalar quantity, the magnitude of our, not the vector, to the kth power, and we have the radial factors, r squared and r here. So this integral, that also can be tabulated, and there's something very interesting about that. I'm not going to write it down on the board. It's in the notes. What you discover is that when k is minus 1, that's the Rydberg formula. That's the energy levels of Rydberg states. So this is going to go as n squared. When k is minus 2, that's the centrifugal barrier, and it's also the interaction of an electron with a dipole. If there were a point dipole on the nucleus, this would describe that. When you get k is minus 3, that's spin orbit. And it turns out for k of minus 3 and all other values of k smaller than 3, you get basically an n to the minus 3. You see, for example, in the k is minus 4, you get an n squared in the numerator, and an n to the 5 in the denominator, that's n to the minus 3. And so for everything of higher negative power than 3, you get this basically, it's telling you all it cares about is what is the amplitude of the wave function near the nucleus. And the amplitude of the wave function near the nucleus scales at n to the minus 3 halves, as I will prove next time, and that's where you get this universal n to the minus 3. You never knew that. You'd never find that in a book. Okay, what time is it? It's time to quit. Let me just do one more thing. Let's talk about the vector model for a second, or a vector model. Suppose we have J here, and L here, and S here. So L plus S is J. Now, suppose we stick a photon in, and remember the photon only knows about L. So we have a choice. We can put a photon in with its angular momentum, because it's like an angular momentum of 1, pointing parallel to L. So we could do that. H2. And what does that do? Well, it shifts S up by 1, up, and so it increases J by 1, propensity rule. Now, if we do this, if we put in the photon perpendicular to L, well, that doesn't shift S up, and J doesn't change. So this simple diagram, as long as L is long compared to S, you get this very strong propensity rule, and so you can understand why delta J is approximately equal to delta L for transitions. There are other more complicated uses of these vectors, but that's one of the nicest ones, simplest ones. Okay, and so I'm going to stop now, and tomorrow morning I will do a little bit of explanation of the n to the minus 3 halves amplitude factor for the amplitude of the wave function near the ion core. That's the beginning of quantum defect theory.
So I'm looking at the notes on page 3, and at the very bottom there's the H1 and lithium-3 and sodium-11 energy levels. And you say that it obeys the z to the 4th scaling relationship very accurately.
I didn't say that. I said it ought to. It doesn't? Or
okay, so this is sort of curiosity. So the exact relationship for the first two should be 1 to 81. And it's actually 1 to 81.967. So basically 1 to 82.
Well, but 30 is, I just wrote 30 down. I don't even know how I got that 30. Whether
oh, really? Okay.
Rounded it off.
How many significant figures is that, man?
All right. So maybe I'll look it up tonight. But and then the other one should be 180, and it's 180.75. So I was just curious.
Where did I get these numbers?
Well, that was one thing, but also, if it doesn't obey it exactly, where else is it coming from? Like, what else could be changing? Because even if you wiggle around the wave numbers a little bit, there's still some deviation. So is it coming from isotopic effects because you're measuring, not just one isotope of sodium, but a few? Like, what's the dominant other thing other than next to the
I think it's relativistic effects. I said spin orbit is relativistic, but there's several levels of relativistic. One is just saying the interaction between this moving magnetic dipole near this charge that produces an interaction that looks like a dipole-dipole interaction. But there is also a contraction of the
thing as it's spinning,
so there's probably the deviations would probably be of relativistic origin. Now, I've been teaching this course for a very long time, and I don't know where I got those numbers.
Mhm.
I probably multiplied z to the 4 and rounded it off. And that's pretty good for a one-electron system. So,
Mhm.
you know, that's safe.
Yeah.
And you know, you got to be a little bit crazy to think that sodium with one electron is going to be relativistic. So
Mhm.
I think I used the formula. I didn't look them up.
So with your selection rules there, is it worth noting that J prime equals 0 and J equals 0 is excluded? I mean, it's kind of a minor point.
Well, but you can get that from this.
Okay. But is it, okay.
You can't have a transition of a vector operator. So you have a system which got no angular momentum. You stick an angular momentum in it.
It's got to have some.
It's going to have an angular momentum.
Right.
So the J equals 0 to J equals 0 transition has to be forbidden
Right.
for electric dipoles.
Does that vector model hold, so that vector model is true when L is large?
I said that, but when I said it, I thought, well, how did where did it?
Okay.
It was my memory unchecked, which, you know, could be wrong. But I think...
But when L is, you know, if it's like an S or a P orbital, then that propensity rule does not hold as well?
When L and S are about the same length, I think that the relative intensity of propensity rule violating a propensity rule obeying transitions are about the same.
Okay.
Okay, and you don't really need this because we can also derive these formulas using angular momentum coupling. And so the matrix, the explicit dependence of the transition probability on J, L, and S that can be worked out in a universal sense. So, but it's nice to be able to say, okay, what's this trying to do? And so anyway, but I must admit, I made that statement without working it out, but I'm pretty sure it was correct. It is correct. Are we content? So tomorrow morning, early, I will attempt to talk about alkali-like spectra and begin bringing in some of the concepts of quantity vector. See you then.